Good morning, afternoon, everyone. I'm Ramakrishna Garine, and I'll be walking you through our research title, Probabilistic Deep Learning in Energy Time Series Forecasting. This is a comprehensive study that explores how different models perform when not only predicting values but also expressing their confidence in those predictions. Let's let's start with the motivation. In energy forecasting, especially with increased integration of solar and wind, we face a growing uncertainty. So that when traditional deep learning models provide a point predictions that are good for accuracy but blind to confidence, this is basically risky. And in practice, systems operate just don't know what forecast is and not sure how the model is. And that is where the probabilistic DL comes into. It gives an ability to quantify both algebraic and data variability, especially with the model limitations. Moving on, our study basically has three main contributions. It evaluates 5 leading probabilistic DL models in the context of energy forecasting. It compares these models across two realistic tasks, show both short-term and long day-ahead forecasting. It goes beyond accuracy to evaluate models on calibration, sharpness, how well they present in the confidence. We have also benchmarked them against traditional models like quartile regression and simple NNs to contextualize their performance. So we have used German electric load, which spans about 2015 to 2019, a record of 15-minute intervals. This data set is comprehensive and includes about 140,000 records. We reserved 80% of the data for training and cross-validation, and the remaining 20% is for testing. We also applied pre-processing techniques like scaling and deseasonation before feeding the data into the models. So we tested the models in two key scenarios, that is short-term forecasting, which is again predict a 15-minute interval using lagged values, and the day-ahead forecasting, which predicts the entire day's load without relying on immediate lagged values. These represent common tasks in the grid operations. Again, the short-term task is crucial for real-time adjustments, while the day ahead is critical for procurement and any sort of planning. Here are the 5 probabilistic models we have tested. The first one is Bayesian Neural Networks. These place distribution over weights, capturing epistemic uncertainty, but are computationally intensive. Next is Concrete Dropout. This is a practical extension of Monte Carlo dropout that learns the dropout rates. The third one is Deep Ensemble. Again, training multiple networks with average predictions is a major one here. Moving to Deep Gaussian process, model is layered uncertainty using GP kernels, but are hard to scale. And the last one is functional NN process, like the neural approximations of GPs, flexible, but training is again challenging. So each has different assumptions and strengths, some more interpretable, while others are better suited for quick deployment. Moving on to the data and setup, the load came from open power system data. We choose Germany because of the large amount of historical data available and the country's significant renewable integration. We have also ensured that pre-processing steps like normalization were reversed after the prediction to understand the real-world magnitudes. Each model was trained and cross-validation against different performance was evaluated on test sets of about 30,000 records. Moving on, let's discuss into the key accomplishments. One of the major significant was important for the recalibration. Many models were overconfident or either underconfident initially. So we used pit histograms. We analyzed how well the predicted in the distributions matched against the empirical ones. Post recalibration, the models showed a marked improvement in the probabilistic calibration. This step is often overlooked, but actually it is essential for making uncertainty estimates trustworthy. Moving on, beyond the calibration, we looked at sharpness, how narrow the prediction intervals are. The sharpest model is one that's most confident without being wrong. So Deep Ensemble and Concrete Dropout consistently achieved high sharpness scores while maintaining the good calibration. Bayesian neural networks are strong too, but they are slower. Functional neural network process and deep Gaussian process had wider intervals and struggle with convergence. Moving on, let's discuss into the results of the day-ahead forecasting. Honestly, the day-ahead forecasting scenario was tougher. Most models exhibited under dispersion, meaning they were either overconfident in the predictions, but however, Bayesian neural networks stood out there. Following the concrete dropout, the pit and marginal calibration plots reveal the persistent bias in the models like the functional neural net process. Again, interestingly, the training time was similar to the short-term scenarios, maybe around 2 to 5 for the most of the models. And again, in summary, Deep Ensemble performed best overall, which are accurate, calibrated, and are fast. Concrete Dropout were most practical for deployment. BNNs provide the robust uncertainty, but were kind of slow to train. FNPs and deep GPUs showed promise, but required tuning. So this confirms the probabilistic deep learning is viable for operational forecasting, again, not just for academic interest. So it gives us both a forecast and the confidence to use them in the future. And speaking about the future work, we are definitely exploring the next steps. To begin with, we are trying to improve the training stability for deep GPs and FNPs, and we are also trying to combine Bayesian and Ensemble strategies for hybrid model. The try attention base for transformer architectures, which have been revolutionized in the NLP and time series forecasting. Finally, we want to investigate the real-time applications and model interpretability for energy operators. This concludes my presentation. Thank you again for listening. I'd love to connect if you have working on similar problems in energy forecasting or deep learning. You can reach out on my LinkedIn, on my email. I'm happy to take any questions. Thank you.